failed
All right. So the last thing we'll talk about, there's a little bit of material in chapter 5
Burn through it, see what you get.
on wood. So this is going to be our spanning elements. We'll just talk a little bit about some things in general, and then we'll look at bending and stress. So what we're going to take into account in this chapter are roof and flooring systems. Okay. So, and we have a variety of wood products available to us. So we've talked about this last semester. You talked about it in Materials 1. I guess those of you who haven't taken that, you'll see it this fall. But we're talking here about 2x4s. Talking about trusses, right, where we have mechanical connections. Glue laminated. Okay, and then plywood panels, amongst others. Right? There's a lot of other items that are available to us. Okay, so the first thing that they lay out for us, just keep dropping right down here. We'll talk about 5.1, okay, and it's just kind of identifying some of the types of structural lumber. 5.2 and 5.3 deal with design types. We'll deal with some of the tables from 5.2 and 5.3, but we're not going to get into ASD, allowable stress design. We're not going to get into a lot of LRFD, the load and resistance factor design methods. You'll use, for one of the homework problems that you'll still need to use that 1.2 times dead and 1.6 times live that comes from LRFD. But so our structural lumber anyway. Okay, so we have the following ID markings, right? So we'll have our wood species. We'll have our structural grade. We'll have the size. Your usage classification, and then the grading authority. Okay, so we need to know from what type of tree did this thing come from? Okay, what structural grade are we looking at? Type 1, type 2? What is the size of the member, right? We need to know that so we can figure out where we're going to put this thing, what its usage classification is, and then who did the grading itself. Other factors. Okay. Why do we care about the density of our wood?
Weight. How strong it is.
Oh, could tell us how strong it is. Terry, what did you say?
Weight.
It's ultimately going to give us our weight, right? We know that we have a certain dimension. We're going to have a certain cross-sectional area. We'll have a certain length. If we know that density, we can figure out what the weight of that thing is. Okay, that's going to be important for our bearing calculations. So basic grain pattern, okay, as the thing is sawn. Why are we interested in knowing what the grain pattern of this thing is?
It depends on how it breaks. If you're going against or with.
Wood is anisotropic, right? So depending on how we orient the grains, it's going to have different properties. Okay?
What is what?
Wood is anisotropic.
Define that.
So anisotropic means that you have different properties in different directions.
All right.
Okay.
Fun stuff, more.
So think about our steel. If we took a section of steel and pulled on it in tension, is the steel going to care how we orient it?
No.
No.
It's going to have the same properties, right? Think about our concrete. If we if we cast a massive block of concrete, say it's 1 cubic yard, okay? And we want to cut out, instead of cutting out a cylinder to test in compression, say we want to cut out a cube. If we cut that cube out, does that cube care how we orient it? We care because we should be interested in how we cast the thing, so we're consistent with that, but the concrete isn't going to care. Wood definitely cares about how it was cut, okay? So we're interested in that. Natural defects. Why are we interested in natural defects? How does that influence the wood? If we have a knot, what is that going to do?
It'll be weaker in that way.
Yep, so it's within the knot itself, you have a localized strong point, right, when you're trying to cut through the thing, but it's always having voids around it, which is causing weak points. Okay, very good. And then what about our moisture content?
We take with like the shrinkage or expanding when it's dry.
Okay, moisture content is going to deal with weight. It's also going to impact our shrinkage, right? Okay, very good. Then they also talk about the 4 major classes of structural lumber. Okay, so item 1 is dimension lumber. What are we talking about when we're talking about dimension lumber?
2x4.
2x4s, 2x6s.
And you can have a number.
Yep, exactly. Okay. What about beams or stringers? And be careful with the stringers. When we're mentioning stringers here, we're not talking about our stair supports. Okay. What are we talking about when we're talking about beams?
Like floor joists.
Yep, could be our floor joists. Yep, yep. Could any sort of spanning material, right? Could be our roof sections as well.
What does that mean about your nominal that you got up there on number 1? Nominal thickness of 2x4 or?
Nominal thickness of about 2 to 4 inches. Nominal width of 2+ inches.
Okay.
Okay.
Beams and stringers.
So here they're saying, so think of your 2x4, you're using your nominal 2-inch side
Yep.
is, in this dimension, your nominal 4-inch, your nominal 6-inch, 8-inch,
Yep.
etc., going in that dimension. Okay? So what they're talking about when they're talking about stringers in this section is as you have a section laid out, okay, your beams are what you're using to pass loads between your columns. Your stringers are the sections running transverse to those beams. Okay? And what are we talking about when we're talking about posts or timber?
Vertical.
Typically vertical. Okay, and usually in our posts and timber, we're going to be interested in how that compression is doing for it. Is it trying to shear anything off on those bearing ends? Aren't typically too concerned about bending with our posts, just because of how robust they are. Okay? Oh, we should say, let's see, that kind of got, stringers got a little away from us. Or here, 5 by 5 or larger typically. Okay. And then what are we talking about when we're talking about decking? Your book
That'd
only.
be, roof,
Roof.
sheeting,
Yep.
or floor.
Okay. What type of materials are we using?
Plywood.
Plywood oftentimes, right? Could be some sort of tongue and grooved piece as well. Okay. So that addresses their identification. The things that I want us to look at are bending and shear. Okay, and so we've talked about this. It has been a little bit, but we can jog our memory back to bending and shear, right? What are we talking about when we're talking about bending?
Bending.
We're trying to use rotational energy, right? What are we talking about when we're talking about shear?
Okay, breaking.
Shear, we're trying to apply a force and use that force to fracture that material in the vertical direction, right? So we'll look at bending first. Some places that you will want to bookmark for doing your problems. You are going to need table A.8 on page 659.
Is this the assignment or is this the example?
We'll go through an example first,
Okay.
but we'll need to reference this
Yep.
for the example, and then you'll need it for the homework as well.
Okay.
So we need for the first problem. Also need table 5.2 on page 193. Oh, that's right, it does give us. And we'll also need tables 5.1A
190.
and 5.1B, which are pages 190 to 191. Okay? And so from table 8.8, you get your dimensions. Okay? That's where you're going to get your cross-sectional areas. It's where you're going to get your section modulus, which I'll explain the section modulus in just a second here. Table 5.2 gives you if you need to make a correction based on the size of the member, which would be a check that we'll do at the end. I'll lay out the problem sequence here. And then tables 5.1A and 5.1B give you stress values for the different material types. Okay, so the different material types that it gives you, 5.1A is a Douglas fir, 5.1B is a hemp fir, yep. So just the type of material that you're using. Okay, we could also look at things like oak and maple. It's just fir is what he chose for this book.
So outside of this, but for that Douglas fir, it'd be cool to say.
I think it would be. I mean, it's going to give you a little bit stronger value than what you're probably going to give you. But
way bigger.
Yep.
So I
Yep.
don't know.
But yeah, I think that it would be fine for getting you your calculations for the
Henfer is
report.
lower, so should I do that?
What's that?
Henfer is the lower one,
I would use the lower one.
so you said, okay.
Yep.
All right.
Okay, so when we're investigating our lumber for structural use, we're going to be interested in a number of factors. Just as we were for steel, just as we would be for concrete. Okay, so we're interested in things like shear, we're interested in deflection, how much is this thing going to displace when we load it. We're interested in end bearing, right? As we compress this thing, as we apply a load to it, what's happening to the ends of the system? We're interested in lateral buckling, which we won't look at with the structural lumber. That's what we look at with the steel, right? As we compress this thing and it starts trying to bend, what's happening to it? But we are going to look at bending stress of beams. Okay, so we'll look at this guy, and then we'll look at that guy. So the steps that you'll need determine your maximum bending moment. And that's going to be M. If it's not provided, you'll need to select your wood species and your lumber grade, whether you're going to use type 1 or type 2. Then you can go to table 5.1. If you're using the Douglas fir, go to 5.1a. If you're using the hem fir, go to 5.1b. Determine your allowable bending stress. Okay, and we'll take a look at that table in a second here and see what's going on there. Step 4 is consider appropriate modifications for the design stress. This is included as it is a step in the design process. I want you to be aware that for the problems that you have, you will not need to do this step. Okay? But it is something that in a real world design application, we would have to take into account.
Yeah. Burner for that one.
19.5.
Yeah, we can get this like stuff we won't use.
Some of them are.
Find the section modulus.
I'll talk about section modulus in just a second.
They got a letter.
Does that have a symbol?
Yeah.
It does have a symbol, Terry.
Of course it does.
It's design, everything has a symbol.
It's probably one we've already used like 3 other times.
There'll be some new one.
Right?
Some-
Squiggly with a line and a circle somewhere.
Yeah, I'm looking at it right now.
No, like,
Environmental test.
I don't know. Like,
Thank you, granted.
I should say, so it's capital S. That,
I mean, capital S.
I don't know.
yep, is your section modulus.
I don't know if I do.
Yep. Okay, so here's the steps that we'll take to jump through our bending stress.
Maybe writing this stuff, man.
What's that?
Hang on.
So let's look at,
pages in this 6-subject note class.
My neat demo-y on leather binder with a notepad. Yeah, burn through that.
Like,
You don't need a notepad.
is there any, pen for?
Simple beans. And burn. And a total.
Okay, so we have a simply supported beam. What are we talking about when we talk about a simple beam? What does it look like?
Straight beam with 2 points.
Straight beam anchored on each end.
It goes on top.
It's been too long since I've drawn it, hasn't it?
It's bush league stuff then.
Day one.
Day one.
Right? Here's our beam.
I'm still trying to write this up.
Yeah. I know what that means.
So is the point of this problem, you're trying to get the smallest beam that will work? Is that what you're saying?
Correct.
Okay.
We want to,
Cross-sectional area basis.
what Russ just said is, what are we trying to figure out? What we want to do is we want to get the smallest beam so that when we install this thing and we load it up, it doesn't rotate on itself, it doesn't pull itself off one of its connections. Okay, so we're right back to our bending problems. Okay? The first thing that we'll look at, we'll need to determine the maximum bending moment. Now, one of the things that we didn't have time to do when we were in the chapter on bending is look at all the different moment equations for our various loading conditions. For your homework, this is the only condition that you will have. Okay? It will be a uniformly distributed load.
Okay.
Okay? One of the problems, you will have a live load and a dead load that you will have to factor. But once you factor it, it's the same problem. Okay, so our moment equation for this condition, M equals W times L over 8. Okay? Here your W is your load and your L is your length.
Why 8? Because it goes halfway, because we're figuring, is that why you chop
I'm sorry, say that
8?
again.
Because it's 16? so
Why is it
was-
divided by 8?
Yeah.
So if we use calculus in this class, we would derive where this equation comes from. When you take the loading pattern of a uniformly distributed beam
It's 8, it's
and you
cool.
integrate it, your factor out front becomes 1/8.
So would that carry for all the problems we're just seeing today?
For all the problems that you're going to use, yes,
Okay.
you're going to have a uniformly distributed load.
And solve them right?
All of them, this is the only, this is the only moment
Talk to
equation
me like
that
I'm
you need.
stupid.
Nice.
Yep, yep.
Gotcha.
So you don't, you're not going to need to use, I'm not gonna give you one where you're gonna have loads distributed here and here and L over 3, L over 3, right? Because remember when we did, think about when we did the flexure calculation for the concrete beam.
Yeah,
We used a different
Yeah,
equation,
yeah.
right? We didn't use,
So
there
it-
we used PL over BD squared,
yeah.
right?
It is not 8 because that's half of 16.
Yeah, see, that's what I was going at. It looks like
Oh,
you're going right in the middle of
I
the
see
beam.
what you're saying.
'cause
I
it's-
see what you're
It-
saying.
it-
No, no, no.
It is half of
No,
16.
it's,
It
no,
is
Well, yes, it is half.
it's convenient
Yeah,
in that for this
that's what I was trying to
problem.
rule out, so if I see 20, I'm
So I
not gonna
got
put
13.
20.
Correct,
13,000?
yes.
You get what I'm saying?
Yes,
13,000?
yeah, sorry, I wasn't picking up what you're saying. So, the question is this 8 because the length is 16 feet?
That
No,
is incorrect.
it is not 8 because the length is 16 feet. So if we change this to 20 feet, this does not magically become 10.
Alright.
This stays 8. So that's due to the derivation of the equation based on the geometry. Right, which-
Asterisk next to that.
Yep.
All ways
Okay?
Wait,
W is your load of 6,500.
W is your load.
oh, okay.
6,500
No,
pounds.
I had it wrong, because you had WL over 8 equals 6,500. You were just starting.
Oh,
that.
yeah, sorry, yeah, sorry, I just
Alright.
stopped, I just stopped writing when you asked the question.
13,000 is
It's
what I
not
have.
junk.
13,000 pound feet, yep,
Pound feet, that's what it is? Okay.
yep. Is it right? What are we talking about?
Load
Pounds
and
and
length.
We're talking about bending, right?
Yeah.
Bending is our moment. So our force times the distance, right?
Yeah.
Like 8 weeks ago. Gone?
Listen to what you just
All
said.
right.
8 weeks ago. You know how much we've done in 8 weeks?
Not a whole lot.
That doesn't matter. It sounds fantastic.
Okay, so,
Wait. That's not 30. Oh. Divided by 8. Okay.
yeah, you gotta divide it by, yeah. You're 26, what was it, 80, 104,000 up there, right? Okay, do we need to select a wood species and grade?
No.
No, it's provided for us, right?
Well, how do you know
Grade.
the grade?
That's from the table? The table will tell you the grade, or?
Table, yeah, and we'll get to that in just a second, okay, so.
So we can just put hem for
So is that the answer?
right
So
now.
your hem for,
That's not the answer. No,
Is there gonna be an answer?
there's going to be an answer, John, yes.
You see, you've broken our trust. Right? So like 2 days of working on something and, oh, well, there's no answer. Don't easily forget that.
So let's take a look at the book. So, so give me a second here to get mine pulled up.
Okay.
So jump to table 5.1. We want to see what are allowable,
That's 5.1B.
600.
or yes, sorry, 5.1B. Thank you.
And
You're a hem for,
it doesn't,
Hemp?
hem, hem,
what's M again?
hem.
M is our,
Okay, and so we want to look at bending. So look at the bending column. Okay? So what are some things that are available to us?
so if you go under
This
beams,
whole table is hemp.
it gives
Yep.
us, because we're a beam, right? A simple beam.
Yep.
So I don't understand what number 1, number 2 mean. but
So
under
that's our
bending-
structural grading. So our structural grading, we can do select, we can do number 1, number 2, number 3. So
So-
as you're moving down, you're dropping in your structural grade. Okay?
So we would need to be,
Go ahead.
well, bending's all very much smaller than what, are we looking at the 13,000?
No, don't try and relate this
Okay,
to what we're looking at. Yeah.
Okay.
Okay?
so do we just get to choose?
Yep, so we want to come up with a choice. Okay? When I work this out, the choice that I made, and it's the same as the book, is they use both the select structural for the dimension lumber. Okay? So we're down here, so
But we're not using we're not using dimensional lumber.
we don't know that.
It's a beam. Dimensional lumber says.
Why couldn't you use dimensional lumber for a beam?
Oh, you mean just stacking a bunch of them together?
It's
or-
adequate.
If it's adequate, does it matter?
Well, because it says beams and stringers right there. So I thought we were stuck to
At
this.
least 2x4s for stringers.
Yeah, I mean, right, but you could still use dimension lumber,
Okay,
right?
so
I mean, we
the
don't
whole
know.
tables are, it's up to us.
Yep,
Okay.
yep. I mean, we don't know what true construction is going on with this thing, okay? So, but yes, Rush, we will also consider the select structural from the beams
Okay.
as well, okay?
I thought since it was a beam, we were stuck to those
No,
4 choices there or whatever
Nope.
it was. All right.
I feel like this assignment should be number 2.
Thank you. I was putting the what if.
I am definitely going to be putting in the one. Man,
I got
it's gonna be,
Sure, we should be using number 3?
if it's gonna be,
Number 3, use table 5.1 to determine allowable bending strength. So you
Yep.
use,
So we've done that, that's where this came from, right? Came out of table 5.1B.
see the 1400. Let's see the 1300.
1300 is just your,
So what would make you not want to just use select structural every time? Why would you select?
oh, I see what you're saying.
You
So,
use the one that would, you, on both of them, you use the highest, why'd you pick those? Just,
it's just easier for an example.
Okay.
So you you don't have the option to use select.
okay.
Why would
It may not be available in your market. It may not be available in your budget, right? As we're moving up from 3 to 2 to 1 to select, we're increasing our dimensional tolerances, right? So we're improving the quality of that wood. What happens when we improve the quality of something? The price is gonna go up on it as well. Okay, so price might factor us out too.
Right.
That might be a thing that, when we make this recommendation, our price may come back and the client may go, ha, very funny. Go back and sharpen your pencil, right? Okay, so. Well,
mechanical?
withdraw more lead then, right?
Use your eraser.
Yep. Okay, so step 4 we're gonna skip, right? We don't have to take into account any appropriate modifications. Next thing we need to do is we need to find the required section modulus. So what we're talking about when we're talking about a section modulus is now we're taking this beam and we're rotating it and we're looking at it, it's coming in and out of the board, okay? So we're saying, based on this bending, what do we need for our thickness and our widths? Okay? But your section modulus is going to be per foot. So your units in S are going to be cubic inches. If you go to table A.8 on page 659, okay, so table A.8. So you see you have, if you go over to the 4th and the 6th columns, you have a section modulus for your x-axis, you have a section modulus for your y-axis. Okay? We also have a cross-sectional area. How we determine this is our section modulus is actually calculated by taking the moment and dividing it by your allowable stress. We should put this in then too.
Allowable stress. FB, is that F sub B then?
F sub B.
Yeah, we're gonna mention that key at the again. So that's F sub B is number 3?
Yes. Okay, so how do we calculate our section modulus?
So we could take 13,000 divided by 1,400
Yep.
or 1,300. I don't know. I guess we're looking for, I don't know what we're really,
Are we looking for something that's just gonna be above 6,500?
that's what I'm,
I mean,
We'll get to that. Let's use our dimension lumber
divided
first.
by 1,300 is gonna be 10. I'm gonna go out on a limb.
10?
9.
We have to be careful, though.
9.3 is that one.
What do you have for units here?
Shit. All right.
100 feet.
What do you have for units here?
So times 12 to the 13,000. All right, so maybe 13. So 111.
Sorry, yes. 111, right?
Yeah. So that would be in inches cubed, or cubic
That's
inches.
inches cubed, right? Because here your pound inches,
Yeah, and you already got square.
here you have pounds per square inch. So your pounds will cancel out, your square inches flip up into the numerator. Okay, so your section modulus is in cubic inches.
So that, the section modulus would actually, so we have 111, but how do we determine, because there's a y and x axis? Are we supposed to be picking one of these?
So that's the recommendation that we'll have to make. Then we'll,
Okay.
yep, that will be the next step that we'll look at. Okay, so if we look at our beam and change this to 1300, this all remains the same, right?
Yeah.
We're just changing this to 1300, so
120.
okay? And what Rush asked is, well, so what dimension do you use? And keep in mind, this one isn't limiting us. It's not saying, hey, you have to install it on the x-axis, you have to install it on the y-axis. We can pick and optimize our size, get it down to our smallest size, and then spec into our plans how to install this thing, right? Does that make sense to everybody? Okay. So the next thing that you'll do is then you'll flip over to A-8.
So you'd want the smaller number. We'd want to go with dimensional number.
Yes.
Because the goal is to get it smallest.
Yep, exactly.
What if it's, I don't know if it's too small.
Don't worry about that.
What's that?
That's how you build it.
But we determined the maximum bending moment, right? So John's question is, what if we make this thing and it's too small? We calculated this number based off of our maximum bending moment. So as long as we don't allow our section modulus to get smaller than the modulus that we calculate based off of our bending moment, it's going to be fine. It's not going to be too small. Okay? Now, if you get down to 109, now you could run into issues. Okay? But as long as you pick a system that doesn't go below your section modulus required for this bending moment, you're not going to fail it in bending. Okay? Now we do have to keep in mind, there's only one aspect of it, right? There's also deflection, there's also shear, there's also that bearing area, right? So there's a whole bunch of things that we have to look at, but this gets us through the most important. So you can certainly feel free to browse through 8.8 at your convenience, but some items that do work, if you look at a 4x16, or if you look at a 6x12,
Oh shit, there's a whole other page.
okay? So what you need to do is you need to find, using your S column, is it the fourth column? Yep.
What, I was saying like.
Or sorry, the fourth and sixth columns. So Rush, what I would do is, as you're looking at the X and the Y's,
Yeah.
find the minimum in those dimensions,
So
right?
y is only 31.
Or the maximum, yes.
The one
You don't-
closest to your number.
Yes.
Pretty much,
Yes,
right?
you want the maximum.
Then it's okay to be over. Yeah, you'd want.
It's absolutely okay to be
you need
over.
Yeah, I got you.
Okay?
So just don't go under.
Don't go under. And then keep in mind that we can say, hey, it needs to be installed in this direction. Okay? Could we work this problem backwards?
No.
Why not?
Because we're not gonna do it.
I'm not saying that we have to, just think about it philosophically. if you only have a certain amount of space to work with, can you figure out how to do this problem? Can you then say, this is how much load we can put on this structure?
I'm gonna say yes.
Yeah, it's just working the thing backwards. Okay?
Yeah.
Because you'll know your cross-sectional area, that's what you have to put the thing into a space. You can use that to generate an S equation. You can figure out what your allowable bending stress is for the type of material that you want to use. Multiply your chord modulus or your section modulus by your bearing stress. That'll give you your moment.
Okay, so we have 111 inches cubed, and we want to find something that's close to that in this table.
Yep.
Why didn't we go with?
John, I will not say that these are the only things in that table that work. There certainly could be other things that work. And so,
Without going under.
correct.
Like there's something with the 112. Why didn't we just do that?
You certainly could.
8 by 10.
You certainly could.
Go down.
Okay?
I don't know where to go.
Nobody does.
So now don't we gotta go to 5.2?
Are we done?
Yeah, then you have to go to table 5.2, see if you need to adjust any of your numbers based on the size of that guy. Okay? 5.2, 193. So 193 gives you size adjustment factors for these items. Okay, based on your grade.
What did we pick? 1?
So
We use,
You don't need to.
look at your 4 by 16. Okay, so you have a width of 4 inches. Or sorry, a width of 16 inches
193, right?
and a thickness of 4 inches
1.0.
for your 4 by 16. So that has a correction factor of 1.0. What about your 6 by 12?
Mm, 1.0. Oh wait, 1.3. 6 by 12. 1.1.
1.1.
Wait, that doesn't work. There's no 6-inch thickness.
Yeah, what are we doing for? Yep, so we'd have to upgrade to we'd have to go to an actual wood design table to get that correction factor. Yeah, what did
Okay,
it have? FC. Yes, sir.
So, what did we just do? The correction factor?
The correction factor, yes.
What is that? How do we apply it?
What is that?
Yeah, what do you?
Your correction factor you'd have to apply to your S.
Yeah, but why?
Oh, so if it's
It's
1.1, we'd
just
have a
based on the
0.1
dimension
different.
of the
So
system.
let's say it was 1.3, right? S would be 1.3, so you'd
You have
times
to multiply it by
111 by 1.3 and see if it still fits
Yep,
in number 6.
correct.
Yeah, where are you getting these?
I'm just saying if it was, it's 1.0.
It's 1.0
Where?
for the 4 by 16.
Right here,
Yeah, I'm looking at the same table.
14 inches wider, right?
Yeah.
16 inches wide,
Yeah.
it's 4 inches. It's 1.0.
1.0.
1 times 111 is what? So we don't have, but if it was 1.3,
It'd probably be more like
Then we gotta type.
115.
yeah, right?
Okay?
And it still works in those two.
And it would still work, so.
That's what I was thinking.
Yeah.
And then that's for the 4 by 16 though, right?
That's correct.
And for the 6 by 12, it would be.
The 6 by 12, the table doesn't give you enough
So 4 by
It doesn't give you
16 is our
information
choice.
for 6-inch dimensional lumber.
But so if the area is, just between those two, 4 by 16 and 6 by 12, both of the S's work, but the area is smaller for 4 by 16, so wouldn't you want to choose that anyway?
You'd want, right, because you're asked to
You're
minimize.
asking for the, yeah.
Yep. So, yeah, as long as your minimum works. You're happy and away you go. Okay?
I didn't do mine yet.
All right.
It's G.
So if I give you a problem like this, be able to mush through it?
Yeah, let's see, what do you got?
Okay.
What are we doing here? Send it on. We got a test to take for.
Did you say this is extra credit?
I'm sorry?
Did you say this is extra credit?
That's what I
I
heard.
did not say it's for extra
I
credit.
totally heard
That's,
that.
does it,
I heard you can do this instead of the report.
I think it should be.
we can go back and look at the video if you want. I'm
Is-
fairly certain I didn't.
Number 2 referring to this assignment right now? Number 2 over there?
Not required.
This step 2
Yeah.
to the assignment.
Oh,
No,
I'm sorry. I had
there was no step
Number 4.
for this process where it said regards to completing the homework.
Oh.
I know I just erased it, but
Yeah, I mean.
we can go back to the video if you want.
Video replay.
Yep.
It's a replay,
Yeah.
not a
We got instant replay in this class. Can't do no shenanigans. It's ridiculous.
Okay, the last item.
Huh?
I have the same thing as you for pay request 1.
Is beam shear.
Billing.
Okay, so
It's like,
generally speaking, our wood is going to be fairly weak when we're dealing with shear, specifically on our bearing areas. Okay, specifically towards the end of the beams themselves. They typically want to try and split horizontally. Okay, remember when we were talking about, well, when we were looking at the concrete's truly bending in flexure, but when it fails, it's more of a vertical shear.
I turned the page for nothing.
Our wood beams are more going to want to try and shear on these edges, okay, based on how they're bearing, how they're being borne upon.
Yeah, this is like the other part of the assignment.
Usually,
You're evil.
I want to be sure that we say relatively. Okay, so shear is typically of concern when we're talking about short spans with high loads. Okay, and the reason it becomes a concern is our shear force will typically then take over from bending. Usually, when we're talking about structural wood, our bending is what's going to govern. But once we start getting into short spans and high loads, that's when shear is going to take over. Okay? There's only one equation you need to worry about.
I like the sound of that.
What's it mean? Shear.
Where V is your shear force, we should say force. Right, so it's in pounds. A is your area in square inches. Okay? For this problem, we're going to have, again, a simple supported beam.
Get it?
No, that was the alert for pay request one. Think yes?
It's slow.
he up there doing some grading or something?
No, wait, you haven't checked your grades for admin?
He's been doing some great.
Did you do paper stuff?
He sure did.
Okay, so we have a
Number
6
one.
by 10
Not the final.
beam made of Douglas fir. It's number 2 grade. Okay? Sorry, I should say. When we resolve our uniformly distributed load, it's 6,000 pounds. Okay? If we have 6,000 pounds, what's our shear value at our reactions?
3,000.
3,000, right? When we have a uniformly distributed beam, we resolve this into a point load. It occurs at the middle. When we do our equilibrium calculations, we find that 1/2 of that load gets distributed to each of them. Okay? So, see, and Terry, you were saying you don't remember anything from 8 weeks ago.
I don't remember doing
You didn't even answer. That was me.
So, how are we going to find our area?
We know 60 times 10.
60.
Is that the actual dimensions?
It's the nominal,
What she gave
so what, 5.5 and 9.5, right?
Why don't we use the table?
Because that's extra work.
It's going to get you, Steve is right. It's going to be more accurate, which is going to get you closer to the answer that I come up with.
Steve,
Right?
shut up.
Just Google it.
You could also Google it, I suppose, yes?
6 by 10 nominal length. Bam.
That's also a good point, Kurt. The advent of the internet, right? Page 659.
Got it.
Now that's where it starts. You've got a 6 by 10, right? Oops.
Exactly what you said.
5.5, 9.5 rush.
But in the column, yeah, in the column, but in the column right next to it, it gives you your actual area, right?
Yeah, 52.25.
Okay.
Come on, man, you get the fuck out of my spine.
Oh my god.
So this is the maximum shear stress that you will have. Where is it occurring?
At the ends.
It's occurring at the ends, right? So that's where we said we're interested in.
So what's the end?
86.1 psi.
This is where our shear is most likely to develop, right? On the ends of our beams. So now we just need to run a check. Does this work for our material? How would we check this?
Look at a chart.
Do you know? Yeah,
190,
exactly.
193?
191.
190, 190, right? Because we're looking at Douglas fir.
Douglas for 190.
Yep.
Alright.
Make sure you look at the Douglas fir, not the hem.
No, Douglas is up here, buddy.
Yeah, not the hem.
So shear parallel to grain?
It's the only shear we have, right?
Yeah, but, yeah, so it works because all these are way higher.
Yep.
180,
Weak.
170.
That's some weak shear,
Yeah.
purely shear.
See that shit?
I see that shit.
So we're good to go, right? As long as your F sub V does not exceed
Good. 2.
your shear capacity, okay, out of the table,
Number 2 grade.
you're good to go here.
So we're looking under timbers.
Yep. And I mean, so Kurt, you could look under the dimensional lumber, but if you meet it for that stuff, you're going to meet it for the higher number too, right? Yep. So yeah, as long as you check your minimum capacity and you're good on your minimum capacity, you're going to be good to go for that material. What if this didn't work?
Then choose.
Sharpen your
different-
pencil.
Sharpen your pencil.
Sharpen your pencil. You gotta sharpen your pencil. You gotta figure out, do you have enough space?
Careful.
Can we put in a larger member, right, to increase our capacity? Or do we have to, yeah, can we change the span length? What is it that, what can we do for this thing?
So it's kind of like part 1, part 2, the bending and then the shear is the assignment. Just make sure.
Yep, so there will be 2 problems for bending, there'll be 2 problems for shear. Okay?
I like it.
The conditions will be the same here. You aren't gonna have to go up and look different equations. You aren't gonna have to change your methodology for the whole.
Alright.
Okay?
I guess we can allow it.
Well, I'm glad to hear that. So that's it.
And then
Well, what's the damn homework?
I'll get it posted for you here. It's oh yeah, I guess I can write it out for you. as well.
We got a final to take. This was what, assignment 11?
What'd you get on pay request 1?
Or what?
Pay request 1?
36.
That's what I got.
Yeah, I
I
think
think
it's
fuck on that.
assignment 11, isn't it?
Yeah. We just did assignment 1. I emailed it to you.
Assignment
And
11.
I emailed it the first time.
We just did 10.
And it said my file was too big, so I had to like redo it.
Oh really?
Yeah.
Weird, because I feel like our email has 5 megabytes.
Yeah, I think because I did a lazy way of putting it to PDF the
Gotcha.
first time.
That's probably
Gotcha.
a good.
And then I was like, no. And like it gave me a message saying that you
No, I
didn't
think that's
receive
the
it because it was too big.
Sure.
This here's the
What's
other
that?
on this side of the lighthouse down here.
Assignment 9 was the lab tour, or the plant tour.
So I was looking here at work 8 and then we jumped to 10.
Okay.
So